today's plan is to work on whatever problems might interest you. I suggested 4. You could tell me what you want to see. You saw the message, right?
Mm-hmm.
Yeah. Oh yeah. Oh, yeah. So there were 4 problems. What do you guys want to see?
3 dice.
Sorry?
3 dice.
3 dice. Okay. Anything else?
The cookie one.
The cookie one?
Chocolate chip?
Oh, the chocolate one. Yeah. That you guys solved, right?
Mm-hmm.
Okay. You think that's fun for
I think that's
people to see?
a good problem to see.
Yeah. And you guys had a chance to look at these problems, remind yourself, yes? Okay, good. So, yeah, so maybe, yeah, let's quickly do 3 dice. I don't want to get into all the details so that you can go and try this. Let me see if I can pull that up. Did you guys try the strawberry banana thingy? No? It's worth it. Yeah, you should. She's also sliced it into 2 if you want to take half. All right, so here is the 3 dice problem. Should I put the problem up on? Well, forget it. So here's the problem. It says that you're given a list of 3-letter words, okay? And your job is to create 3 6-sided dice with letters on them. The letters will come from the words, but they have to be in such a way that for every word that you are given, each letter is on a different dice. Is that clear? That's the problem. So let me show you an example. Here's an example. If you're given lad, fin, and sly, right? Then you could do that with these 3 words. Again, there are some letters that are not on any of the words, which is okay. If you run out of letters, you can add whatever else you want. But no letter can be on more than 1 dice. Okay, can only be on 1 dice, on one side of that die. And so here you have ZOUNDS on the first dice, PLIGHT on the second, and freaky on the third. You'll see that if you want lad, you'll have L in the second word, A in the last word, and D in the first word, right? If you want fin, F is in the last one, I is in the middle one, and N is in the first one. Then sly is in S, first word, L in second, and Y in the third. So it satisfies the constraints of the problem, and so this solution should be acceptable. Okay. And you can output any solution you want as long as it satisfies the constraints that are given to you. If this is your word, then there's no way to put 2 letters on the same dice, and so it's just going to be a 0. Okay. You can also envision problems where you have too many words and there's just no way to achieve the constraints that are needed. Okay? Here's a more complicated example. And you can verify that that solution works for this complicated input. Okay? So you can take anything you want. Let's say you look at tau. Tau has t on the first word, a on the second one, and u on the third one. Okay? So did you guys try this?
We were working on it,
Yeah.
but we didn't finish it.
Okay.
There's a reason why, but
Okay. All right, so what do we do? You guys have read the problem, so any thoughts on this?
try every possibility.
Right, so really this is exhaustive search, and why do you think it's exhaustive search? Were there any clues in the problem that suggest that that exhaustive search is an approach?
There's only 3 dice.
There's more. So if you look at the problem, I don't know if you have that open somewhere. Is there another clue?
Has 18, like 50 dice.
Okay, so 18 letters suggest that, okay, the number is small. There's one more clue. It says that the time limit is 5 seconds, which is actually much higher than the time limit for most problems. That's, you see that, you know immediately this thing is, they just want you to do exhaustive search, brute force. Now, the question is brute force going to work, and what's the right approach? There are 26 letters. All right, there may be, let's say there are 18 letters. Even to try 18 letters on 3 dice, if you want to try every possibility, theoretically there's 3 to the power 18. Right? That's, is that something that's going to be possible? Well, it turns out it's not quite. It's going to be borderline. It's not going to work for you. So 2 to the 18 is, 2 to the 20 is about 1 billion, right? So this is going to be a little much bigger than that. So even if it's 2 to the 18, it's going to be somewhat borderline. 3 to the 18 is going to push the envelope. Probably it won't finish. So just brute force trying all possibilities is probably not going to finish in time, not in 5 seconds. So perhaps you have to somehow make that exhaustive search smarter. And that's what we're going to look at. And pretty much there are all the clues in the problem suggest that this is the way to go. You have to figure out how to do a brute force, but how to do it a little more smartly. Okay? So what are the smart things that you can try? Yeah?
Whenever you're trying to assign a letter to a die, kind of check with the words if there's some conflict.
So you could check for conflicts, and that will help to pare down. So any exhaustive search is basically a big tree, right? You start with the possibility for the first letter, then you try all possibilities for the second letter, the third letter. So you could do exhaustive search on the letters. All right, and it turns out that that's not exactly the best approach, and I'll explain that a little bit later. So what we're going to do is to create a graph, and then think of this as a graph coloring problem. How many of you have never heard of graph coloring? Okay, so you know what a graph is, right? A graph coloring problem is where you assign colors to the vertices of the graph in such a way that neighboring vertices get different colors. Okay? Now, I could take all the letters and assign them colors in such a way that if they come in the same word, then I should make sure that, no, they should not be the same color.
Yeah,
right?
The dice, so the word is on.
So think of each die as one color. If you put that letter on the first die, we'll call it color 1.
Yeah.
If we put it on the second die, we'll call it color 2.
Yeah, so
If we put it on the third die, we'll call it color 3.
Okay.
So if it's in the first word, like let's say aft, then we want A to be one color, F to be a different color, and T to be a third color. Does that make sense? And if we can do this in a way that everything is consistent, then we are done. Okay, so we're going to think of this as a coloring problem. That's one way. There are many ways to do this. This is how I like to think, yeah, about this. All right, so graph coloring is a way to go. And in the end, we want it to use 3 colors. Okay, so you can use only 3 colors, and you want to color all the 18 letters that you may have. Of course, you may have less than 18 letters, but that's okay. So we want to create a graph where the vertices, the vertices are alphabets, yeah, letters of the alphabet. And if you have an edge between 2 letters, it means they're part of the same, somewhere they're part of the same word. Okay? And so every word gives rise to a triangle. And we want to use only 3 colors. We're only allowed 3 colors. And we want to be able to color everything in the graph in a consistent manner. And the consistency simply means that neighboring vertices get different colors. Okay? And 1, 2, and 3, they're not important, they're just names. I can call 1 as 2 or 2 as 3, and it doesn't matter, right? All this is clear? Anybody didn't understand the setting that we have? All good? Okay, so now, I added a little thing at the end that says that we're also going to build a graph on the triangles, basically on the words, because in the end, in order to check for consistency, you have to know which letter is part of which triangle and which triangle intersects with which other triangle. Okay, or if the letter is in this word, we want to know which other word shares a vertex with this triangle. Yeah.
Wouldn't we already have the triangles inside the graph we are making?
We would, but to have the triangles itself as being vertices is a different graph, right?
Yeah, I understand it's a different
Yeah.
graph. Why do we need it?
Technically you don't need it, but for a lot of the search things, it'll be faster.
Okay.
So it would make sense to build another data structure that helps you to also go from word to word. You can try without it. Maybe it's fast enough already. Hard to say. But if you need more speed, this is something that could improve things. Okay. So we already understand that we are looking at a coloring problem. So this is the coloring problem. It says this is, well, first I mentioned this already. This is an exhaustive search problem, just because there are enough clues there in the problem itself that suggest that this is the way to go. Okay? And we also know that 3 to the 26 or 3 to the 18 is not going to work, so we can't just try every possible color to every possible vertex. That's not a good idea. So what we can do is set up over here. I can take one of the triangles, okay, meaning one of the words, and just call the 3 letters as color 1, color 2, color 3. So the first word was it was aft. We're just going to make A as color 1, F as color 2, and T as color 3. Okay? And it turns out it doesn't matter because these numbers are just labels. And so since nothing has been colored so far, I can arbitrarily color this and it would be perfectly all right, right? So I'm going to take one of the triangles, and this is where it helps to pick a triangle that is somehow has intersection with the most number of other triangles. And so you can actually speed things up by having this graph on triangles. So you were asking about that, and maybe there are some extra analysis of the words could be helpful for you. So if I start with coloring one triangle, it immediately says which other triangles will be constrained. right? So, so we can actually go back to this. We can look at this example here. Here's an example. I've got LAD, FIN, and SLY. This is a simpler example. We could have done this by hand, but let's just do this using our strategy. I'll take the first word, LAD, and I will color it as 1, 2, and 3. Here I called it red, blue, and green. It doesn't matter. These are arbitrary colors. Okay? So now all I have to do is to take another word and see what kind of constraints are imposed on it. Now, what are the constraints imposed on SLY? Well, only one letter is the same. So that color is already fixed, which means that now I only have to color 2 other vertices in that triangle, right? So I'm left with S and Y. How many ways can I color S and Y now? There are 2 ways of doing it. I can either make S as blue and Y as green, or the other way around, right? S as green and Y as blue. And because it's exhaustive search, I'm just going to try both. Okay? And so essentially, I'm going to go word by word and attack this. And then I go to fin, and even with my first choice of putting S as blue and Y as green, fin doesn't conflict with anything, and I can just arbitrarily assign it. And even the first shot works. So this assignment already gives me an answer. And since I need 6 sides, I'm going to arbitrarily fill over here any of the remaining letters. So A is here, so I'm going to put B here, C here. D is already here, so I'll put E here. F is here, so I'll put G, H. I is here, so I'll put J. So it doesn't matter what I put there. I'll just give other letters for the remaining corner sides of the dice, and I'm done. And all I have to do is to spit out those answers. Does this make sense?
So each time we insert a letter, we check every single one of those.
So yeah, that's the part that we have to think about some more. And I'll show you another example. We have a more complicated example, and hopefully some of those challenges will become more clear. Now let's look at the second example. Sorry, the second example was trivial. It was DAD. And there's no way to put D here, A here, and D somewhere else, because every letter needs to have only one color, right? So right away it's gone. So this approach works for that as well. So let's try this more complicated one and see how we're going to get this color assignment. Because if we get the color assignment, we're done, right? That's clear. Correct? Okay. So let's say we start with aft. So here I am. I'm going to make A as color 1, F as color 2, and T as color 3. Again, this is arbitrary, and it's perfectly fine. I never have to change this. I can fix this forever, because this is the first word that I'm looking at, right? Okay. So the next one is, well, again, it makes sense to order these words in some reasonable way based on how much overlap it has with the first triangle. And this is why I was saying it'll help to understand, pick a triangle that has the most number of neighbors, and then pick the one that overlaps with it the most. So if you look at FAR, that has the most number of overlap with this. A and F are fixed. So I know that for FAR, this is the only choice I have, right? Is that clear? So essentially, I've now taken care of aft, and I've taken care of far. Okay, let's look at the next one. That's tau. Well, tau has T fixed and A fixed. So T is done, A is done. U is the only thing left. So I've now taken care of 3 words. Okay, what's next? I'm going to pick rag, again, because R and A are already accounted for, right? So R is set, A is set, G is over here. So we've taken care of one more word. So we have to take care of how many words? 4, 8, and 3, 11 words. So let's keep going, because it gets interesting only after a while, right? What's next? We've got ERC. ERC has R, but it has only one, so it's not like it's going to be fixed and set in stone, right? So we set R, but then we don't know whether to put I here and K here or K here and I here. One of these is, well, it's possible that one of them doesn't work, or it's possible that both of them don't work, or it's possible that both work. We just don't know which one. So we just have to try both possibilities. So we're going to, if you want to think about a tree, here's what I'm going to do. I'm going to say A is 1, F is 2, T is 3. So I'm going to make a tree essentially, okay, of possibilities. These are all fixed. In fact, A, F, T, R, U, G, all these are fixed. So G, U, and what was the last one? R, right? All these are fixed. We know what their numbers are. But now I have I and R, and I don't know what I want to do. So I will actually get, I'm going to draw the R over here again. I can get two possibilities, I and K, or I and K, where I will be either 1 and 2 or 2 and 1. We just don't know which one's going to work. Okay, because R was 3 for ERC, these are your only two possibilities. Okay? So think of this as a branch in the tree of possibilities, right? So remember, this is going up, yeah? We just have to try both, and it turns out that there is another word here that will help us figure that out. And that's the word kit. And kit will have K and I to be different from T. And because, sorry, so how did I do this? Oh, it's not going to be a problem with kit, it seems. Yeah, so the problem comes somewhere else, looks like, is it? The problem comes with VIA, not with kit. Kit is easy. So with VIA, what happens is,
Even for VIA, we have two choices, right? Only A is fixed.
Oh, yeah, but I is also fixed here, right?
Okay.
So two things are fixed. If A is 1 and I is 1, you're not going to get a choice for the V. So this whole branch is now to be thrown out. Is that clear? So therefore, this is your only option, and therefore V has to be color 3. Okay? So you end up throwing away some branches in this process, and you'll chop off some branches and continue searching. So we've now taken care of VIA. We have to take care of, we have another 5 words left. You go to UK or UK, I'm not sure. K is set because we decide to make that to be 1. And so K is actually going to be here, I is going to be here. So therefore, this also is not right. It needs to be flipped here. K needs to come here because it's been set there. So I actually made a mistake here, looks like. So K is 1, right?
You have already fixed U as 2.
And U is also fixed. So actually, this whole thing is just was a mistake, was a typo. So this needs to be K and U. And U is fixed. So we are only left with E to be, U is what?
U is 2.
U is 2 and K is 1. So therefore, this must be, E must be 3. Right? So that takes care of that. Kit is, in fact, kit has all 3 set already. You just have to verify that it's 1, 2, and 3, and it's all fine. Then we have cog. Cog has a G set, but O and C are not set. So you have 2 choices for C and O. G is what? G is 2. So C is going to be either 1 and O is going to be 3, or C is going to be 3 and O is going to be 1. We just don't know which one will work. We'll try this branch first, and if that fails, we'll go to the second branch. Okay? So remember, we are building a large tree. It doesn't have too many possibilities because we keep using up 2 letters at a time typically. And the number of possibilities are fairly small, and I'll prove to you that it's going to be small. So we've got cog. What else is left? We have own and yes. So O is now set. W is not there. N is not there. So again, W and N will give you 2 other branches, and then you have yes, which has E set, but Y and S are free. So essentially, the first branch will work. It really doesn't matter. So you can see that it's going to work. And as long as you can color all of them consistently, you can stop there at the first time it all works. Okay. Now, why should this approach be computationally tractable? That's the thing we have to figure out. Okay. And over here, what you need to understand is that there are how many letters to deal with? 18. Okay. It's not 26 because it's 6 times 3. So there are only 26 letters to deal with. And whenever you deal with a triangle, at least one of the letters is going to be already colored. If none of them are colored, that means it's a completely independent part of the graph that's disconnected, and I can take the first triangle and color it arbitrarily 1, 2, and 3, and I never have to change it. So I can fix it.
How can you make that assumption? Because you have a certain number of assignings you already did. So it should be...
Well, if it never touches anything, so I do have to take the original, that's why I need the graph. If the graph is disconnected, I'm going to first finish that connected graph and then go to the next one.
But so even though it's connected graph, you're still assigning some letters to some dice.
Correct.
So if, let's say for the first component, you choose 1, 2, 3 for the letters in that order.
Yeah.
In the second component, if you
I
keep
can.
the same order,
They are completely independent. Choices here and choices there. I can relabel 1, 2, and 3 on both sides, and it won't make any difference because there are no connections. There are no inconsistencies that can arise from
you're
them.
saying after the fact, 1, 2, and 3 doesn't mean this dice specifically?
It means though that die specifically, but what I'm saying is if I have 2 disconnected pieces in the graph, let's say this is one graph and this is a subgraph and this is a subgraph. There's no edge from here to here. So I have a bunch of letters here and a bunch of letters here, and nothing here is on the same word as anything here. If that happens, and let's say that I come up with some coloring 1, 2, 3, 1, 2, etc., and I come up with some coloring 1, 2, 3, 1, 2 independently over here, I can change the numbers 1, 2, and 3 to, I can permute the colors and still get a consistent answer. It won't make any difference. Because ultimately, it's not like you need to have words. Those don't have to be words, real words. They're just fake combinations. Yeah?
There's one more constraint, which is that the number of 1s and 2s and 3s that you assign should be 6 each.
Yes, that part is true.
That part is not guaranteed. If they're not disconnected.
Well, because I never use anything else, oh, I see.
Yeah.
Is that ever possible?
It can be possible.
It is possible. So with 18, it's possible that you end up with a third one. But again, it all has to happen within one connected component. It's never going to be impacted by a different connected component. You're right. So I should add that constraint saying that the number of letters with each color is exactly 6. Sure. Or less than 6, sorry.
Yeah, then you just permute the colors in the another connected component.
Yeah, I mean, they're independent choices, so I can restart the whole process. I can take the first triangle, color it 1, 2, 3, fix it for good, and then work on what's remaining. Cool? Now, how big is this tree going to be? That's the question that we have to ask. Okay. Remember, this tree has exactly 18 nodes, right? There are only 18 letters, right? Now, There are branches, but there are at most 2 branches. You never have 3, because everything comes from one of the vertices being common in some other triangle, right? If 2 of the vertices are common, then the third one is fixed, so then it's no branch. If only one of them is common, then I get 2 branches. So it's like a binary tree essentially, right? Now, how many times can you branch? Because the more you branch, the bigger the tree gets, or the bigger the number of possibilities gets, right?
Branch for each word.
So it's branch for each word is a problem because there are lots of words. There could be up to 1,000 words according to the problem, if I remember correctly. Is that correct? How many words can there be?
1,000.
Yeah. So words can be too much. That's not really what you want. Instead, what you want to see is if a word forces you to branch, then you get only 2 branches, but it forces the colors on 2 other letters. And so you are now reducing the number of letters by 2, which means you can only have at most 9 branches. There are 18 letters. Each time you take care of 2, so therefore you cannot have more than 9 branches. Done. Does that make sense? So if there are only 9 branches, you can have only 2 to the 9 possibilities, which is less than 1,000. No problem. We can handle that, right? And so you do exhaustive search using this approach. It's going to be tractable. The only thing that you have to do is after every time you finish coloring the next thing, you have to go and check the consistency thing. So there's some work involved, but it's still only a linear time increase in the time complexity. Does that make sense? Is this not how you guys approach this?
I made the mistake
Somewhat.
of I was doing like analysis of how many combinations you can have, and I even
You
told
just look
Demba-
like too large.
I told Demba that it was 26 choose 6 times 20 choose 6 times 14 choose 6, but there's only up to 18. If I'd known 18, I would have done exhaustive search.
But 18 choose 6 is already too much.
No, 18 choose 6 times
Is roughly 18 to the power 6, roughly, which is 20. So even if I take 15 to the power 6, even if I take 10 to the power 6, then you have to multiply it by another 10 to the power 6, another 10 to the power 6. I don't see that happening.
the number of combinations. I think it ended up being like 17 million in total, and that's before any pruning was done. Anything under 300 million is fine.
Okay.
Anything else 300 million?
Yeah,
For 5 seconds.
for 1 second. For 5 seconds, you can do maybe
Even more.
900 million.
Yeah.
Well,
Well,
what are the solutions that you put in finish it? That's
No, I didn't. I assumed something incorrect, and because of it, I disregarded it, and I worked on something else. I should have worked on it, but
But I think this approach really will cut it down quite a bit. I think it's roughly 1,000 possibilities, and for each one you'll probably have to look at 1,000 words. So I'd say this is extremely tractable in the amount of time. In fact, it may even run in less than a second. Now, question is, can you guys actually program this? Whatever I just described? What part doesn't make sense?
I got lost once we started the ranking part. So after that.
Well, okay, so let's go through the branching part again. I looked at this and I said A is going to be 1, set for life. F is going to be 2 and T is going to be 3, set for life. No change, okay? Because the first triangle always is set for life. Because 1, 2, and 3 are arbitrary and I don't care, right? Then I looked at AFR and I said, oh yeah, A and F are already set, so it's only R, so there's only one choice for it, and so I'll make that also set for life. So all these are now set for life. This, and this. Okay? So you can think of this as a linear tree, essentially, so far, because I had only one choice. Then I have this, and here A and T are set, so it's only U. Again, no choice. Then A, G, R, it's only G, no choice. So far, I've colored 6 of these guys. I've given them colors, and these are set for life. I never have to touch them again. The next one was ERK, and only R was set, but I and K, I could either go, because R was set to 3, I and K have to share between 1 and 2, because they're forming a triangle with R, right? So either I gets 1 and K gets 2, or I gets 2 and K gets 1. These are your only 2 possibilities. So in one branch, I'm going to go I1, K2, or in the other branch, I go I2, K1. Clear?
Yeah.
Now, later on, I'm going to follow this branch, and later on, I'm going to figure out that this is not going to work, because the word via has I to be 1, A to be 1. That's never going to work out, right?
And what do you do, like,
When that
what do you
happens.
do in the tree when you figure it out?
So somewhere here, down here, I'm going to figure that out. I'm going to work my way backwards to the I and the first branch after it, and that's where I'm going to just chop off that branch.
Okay, and like what, I guess what made you, like what are the things that you're checking that you're like going back to?
No. So look, as I go through this branch, if I make it all the way down, if I end up coloring all the letters, I'm going to declare victory and go home. Okay?
Keep
I'm
that
just,
branch.
sorry? I'm just going to keep, no, in fact, that's all. I don't even need to explore another branch, because the first sign of victory I can stop, right? If I can successfully color all of them, I'm done. Nothing more to be searched here. But if it dies somewhere here because there was an inconsistency, like the word via, at this point, if I start to look at the word via, it's a clear inconsistency, because if I work my way up to the top, A is 1 and I is 1, that's never going to work out for via. So I follow this until there was a first branch after either I or A, and that branch I'm going to just chop it off, snip it. So this whole branch disappears.
Yeah, I understand that conceptually. I'm just like trying to think about how the code would do that.
Yeah. Well, so the code will just go back and backtrack to the first point where there was a branch after either I or A.
But you need to dynamically implement a tree, right?
Yeah.
Yeah.
I think I just.
Well, it's again, you can, if you think of this as a recursive call, then it happens automatically. You just have to declare failure all the way up here.
You need to undo your work, right?
Yeah.
In that recursive call.
You could do that using a stack by itself, or you could do this recursively. So there are multiple ways to do it. Yeah, you may need some help with that piece. I agree.
Remember the traveling salesman code?
Yeah,
It will be very similar to that.
that's right.
Okay.
There's no real. It's like the tree does not.
The tree doesn't have to be explicit. You're right. He's absolutely right. Right? You okay with this? Do you think you can implement this roughly? Pretty reasonable chance?
Maybe, I don't know. Maybe I can.
No.
But I think I can implement it, but
You have to think about where you have conceptual difficulties. Not a question of, maybe, maybe not. That's not how you want to think about this.
I can understand it conceptually.
Okay. Okay. Are there places where you think there are challenges to implementing it? That's the question you want to ask yourself. All right. And if you see some conceptual difficulties, this is a good time to bring it, and we can talk about this. Yeah.
You will use a graph, or rather using a tree will be more.
It is a tree. It's not a graph. The graph was for the letters to figure out what conflicts with what. Here it's just a tree. This is a tree of solutions, right? Of color assignments.
So like while the output you just like 6 letter space, 6
Yeah.
letter space.
So if you think of exhaustive search. Exhaustive search will do the following. Okay, you'll start with A getting 1, A getting 2, or A getting 3. Okay, the next thing will say F getting 1, F getting 2, F getting 3. So you will have 18 such branches. That's why you'll have 3 to the 18 possibilities, and one of these is going to be right. Okay, or more than one of these is going to be right. And your problem, if you can search through this exhaustively, then you can solve the problem. No problem at all. It's just that there are too many branches. There are 3 to the 18 branches. And I'm claiming 3 to the 18 is too much. And you can chop off a lot of these branches. So for instance, if A is 1, there is no point in looking at F equals 1. So already you can start to chop off things. Okay? And there will be similar things later on where you'll say, oh yeah, 2 of these branches are not going to work. Things of that sort. Wherever you see some inconsistencies, you can chop off there. So it's a matter of pruning this exhaustive search tree. So this is called the exhaustive search tree, where it tries every possible color assignment to the letters. Okay? But we are doing it even more smartly by saying, at least for the first triangle, I don't even have to worry about it. It's not like A needs 3 possibilities. I'll just fix A to 1. I don't have to care, right? And not only that, I can even set F to 2 and I don't have to care, because all the rest are going to be symmetric. Okay? So we can prune a lot. Essentially, this is a very, very pruned search tree, because I've set A to 1, F to 2, T to 3, and then I've seen what else gets forced, and I put them down, and then I continue. And when it's not forced, I'm claiming that you get only 2 branches. You don't get 3. 3 is very expensive. 2 is more manageable. And also, when you get 2 branches, you end up assigning to 2 of the letters. So you're chopping off 2 at a time. Okay? And all that makes sure that of these 18 different letters, you have only at most 9 branches, or in fact at most 8 branches, because you've taken care of the first 3. So you have 15 left. 15 can have at most 7 branches, in fact. So 2 to the 7 is really what it is, which is what, 128 or something like this, ridiculous like that, right?
You have to store one data
Sorry?
like one data structure where like each letter gets fixed, like you have to store, right?
Yeah, well, this is what he was saying. If you use an approach similar to what we did for the traveling salesperson problem, essentially you write in the position for A, you'll say that this is the color. Yeah. It is worthwhile for you to think about how to implement this. It's sufficiently challenging that it will test your skills, and there are people who can help you. What do you think? You think this is reasonably implementable?
I think this is reasonable.
Yeah.
For the people that have never done exhaustive search, look at the 8 queens problem.
Yeah.
And go from there. Study that, because if you're going to do exhaustive search and you don't understand the tree structure, that's the first thing you should look at.
Yeah.
But this is
good.
Not
Yeah.
that.
Okay. How am I doing on time? I have 20 minutes. Okay. Well, so which other problem do you want to see? Well, there was another one somebody mentioned. Which one? Chocolate. Oh, chocolate. Yeah. That reminds me, there is food. So the color tubes problem is easy? No?
I didn't even try it.
You didn't try it?
No.
I thought you solved this.
The color tube? No.
No?
I looked at it and it said there's no way I'm trying that.
You want to talk about that?
We can.
Okay, here's the color tubes problem. How many of you remember this problem? Remember this? Okay. So here's the problem. You're given a bunch of tubes. In fact, you're given n+1 tubes. Each one has 3 colored balls. Okay? And you have 1 spare tube. And there are exactly exactly n different colors here, and there are exactly 3 balls of each color. Okay? And your job is to sort it so that each tube has only 1 color. And your valid moves are, you can take any ball from the top and move it to any tube that has space in it. And each tube has only 3 spaces. Okay? And you can only put it on top. You can't put it in the middle or in the bottom or something like this. You can't mess around with it. Clear? So here's one where you have 3 yellows, 3 whatever gold, 3 reds, and 3 blues. Can you do this?
Reminds me of the Tower of Noah.
Yeah, but it's here there are colors. There it was sizes. Yeah, sort of. Yeah. So for instance, what would you do here first?
Make the last one single color.
Sorry?
Make the last one single color.
Which one?
The last, the open one.
Which one? Which color? You really have to think about this?
Yellow.
No, like anyone. Like
It's not any one. You can't move any ball. I can't move a blue one. I have to move only the top ones. So which ones will you move? Yellow. So the 3 yellows go here. Yellow's done. Now I can move this away, and then I can take these 2 extra balls and put them here, and now I have 1 less tube to deal with, and I still have the spare tube, right? And then what am I going to do? Well, it starts to get more interesting at this point, right? So the approach is to take one of these colors and see if you can separate it out, and then move that tube aside and see if you can work with the rest, because now you have reduced the problem from n to n-1. Okay? Question is, can we always do this? And how many moves are we going to need to do this? That's the question. Okay? So how do we approach this? Well, we saw one example. If we have 3 yellows on top, done. We can take care of that, right? We can definitely reduce the problem by 1. What if that doesn't happen? Well, it's a little bit more of a headache. So it turns out that this is basically a case analysis. So I'm going to write down for each color a configuration. If it says 1, 1, 1, it means that color X is on the top of 3 of the tubes. Okay. If it says 1, 2, 2, then it means one of them is on top and 2 others are on the second position in some tube. Okay. So I can then use this to figure out how to separate out one color. Okay. And my goal is simply to go from n to n-1, because then I can simply repeat it. But I have to keep track of how many moves I make. Remember, I don't have to optimize my number of moves. That's what the problem says. You remember this? So it says that I don't care about optimizing it. In fact, what does it say?
20n.
You just want to make sure that you don't make more than 20 n moves. Which means, in order to go from n to n-1, I can use how many moves? 20 moves, right? So I have 20 moves in which to nicely separate out one of the colors. That's my job. So I have to write code for this, and then I'm done. And then I reduce the problem to n-1 and keep going. Okay? Now, the headache is, the challenge is that there are lots and lots of cases. But let's see if we can somehow summarize those cases. Okay, so here is a case table. So let's start with 1, 1, 1. Okay, so I'm going to call this 1, 1 prime, 1 double prime, which means it's 1 on one of the tubes, one on some other tube, and 1 on some other tube, right? So let's say I have 3 yellows on top. I'm going to take all the 3 yellows, move it to the spare, right? And then there is going to be some other tube where I have not removed anything. Let me draw a picture here. Yeah, thanks. Okay, so let's say that these 3 tubes have a same color on top, XXX. Here's a 4th tube that has 3 balls in it of some strange color, and somewhere here is my spare. Right? So my plan is you take the 3 yellows. Here goes 1, here goes the 2nd, here goes the 3rd, right? And then I have one other tube that's full. I'm going to take that and move it here, here, and here. How does that help me? Well, I now have a yellow tube that's all X, and I have a spare tube, and I have only n-1 tubes left. So in 6 moves, you can count this. In 6 moves, I went from n to n-1. Is this clear? So that's going to be our objective, and the rest is all case analysis, trying to figure out how this is done, and also to figure out how to take care of exhaustive cases. Is this clear? So far, so good? Okay, so let's do 1, 1, 2. Okay, so I have 1 here, 1 here, and it's the second one here, right? So this is XXX, and there's some other guy here, and there's a 4th one which is full of some other stuff, and here's my spare. So here's the plan, and it's kind of explained there. You take this and move it here, you take this and move it here, and you take this and move it here. Okay, that exposes this guy, and he can go up, and she can go down here, and now you have the yellow tube. And what else? So I have only 1 left here, and I'm going to take that and move it here. And you can count again. I think it should be 5, right?
That's fine.
It's only 5. So in 5 moves, I was able to achieve this. Clear? All right, I'll let you figure out some of the rest. Why don't you help me with 1, 2, 3 without looking over there? So I got 1, 2, and 3. So 1 is here, 2 is here, and 3 is here. And I got stuff there. What would you like to do? The first one is easy, perhaps, right? So I get this over here. Top one to this empty one, right?
Yeah.
That exposes this. I assume that's what you want to do. And then what?
Top 2 to the empty.
So I take the top 2 and move them here. And that exposes this. And we have an empty box here, and we're all set. So you can try playing with the other cases. It turns out they're all manageable. I tried them all. You're welcome to try it. And you just have to figure out which of these cases you want to apply. Now, in all these cases, I've set one of them to be a 1. Why am I doing this? I'm going to pick something that's on the top row. There's no point in looking at 2, 2, 2. It just is unnecessary work. Is that clear? Yeah, so what?
So like let's say in the first row if I get yellow, on like 900 or somewhere they have like at the bottom you have the other two yellows, then it won't be like searching each top, it will.
Did any of my analysis matter how many tubes there are? I have to just go and find it, of course. So you have to build some data structures to know where my third yellow is and where my second yellow is. And once you do that, you can build the configuration. For every color, I'm going to build a configuration that looks like that.
Can do a linear travel.
Yeah.
Get the configuration.
Yeah. In one shot, I can build all the configurations.
Yeah.
Right? So for all the n colors, I build the configurations, and then I'm going to pick something that has a 1 in it all the time. Simple. Yeah? You believe this? I didn't see any of these go to more than 9. By the way, 133, you want to try this? That seemed like the most expensive one. We can try it. So I got 133 means that one of them is in position 1 and 2 of them are in position 3, right? Is that clear? Okay. So I got this, and I have to figure out what to do. How do I achieve this? So clearly, you probably want to move this first, right? So let's do that. What's next?
Move one of it to the empty.
Move one of these to the empty place. Then
Move these two to the last one.
the second one to the last one. Okay. Then what?
Then I think second one to the last one. Second.
This guy here to that?
No.
You're saying the last second. X.
Second X.
Second next to this last position.
Yes.
Okay.
Yeah. Then the 2 to the
Then the
previous.
Third.
These two over here.
Yeah.
Okay. 1 and 2. And
the
then
top one.
and then you can move this back here.
Yeah. And
Then this guy over here. And then that one over here. Cool.
Yeah.
So how many moves? Did you count? You're going to trust my numbers? Really? I wouldn't.
Count that.
Sorry?
We counted the arrows.
Yeah, you just count the heads of the arrows. Yeah. So it's 1 and 3, 4, and 4 and 3, 7, and 2, 9. So this is the worst of the cases. 1, 3, 3 is really the worst. And I don't care where it is. I can pretty much achieve what I just said. Right? Oh, yeah, by the way, I have to make an empty box at the end. So there may be a couple more, is it? Or is already one engineered? Oh, the last one is empty. Yeah, okay. All right, cool. Yeah, so you may need 1 or 2 steps extra in order to empty out one of the tubes. So, but I thought I counted them. You're welcome to count again. So this is what I claim. In fact, I think that there are only this many possibilities. These cases, by the way, what are these?
Oh, we have 1, 2 in the same.
In the same tube, yeah.
I mean,
So
then
if-
it's easier.
Sorry?
Then it's easier.
It's slightly easier, but then if it's 1 and 3 in the same one, then it's a bit of a hassle. You can try this actually. So there are quite a few cases. So let's say you have here, and let's say the third one is here. What do you do? So I'm going to put some other balls here, and this is my spare. Move the top one over here. That's what we always seem to do. Next.
I mean, I think it would be better if we start with the 2 and expose the bottommost one.
Okay, very good idea. All right. Yeah. Okay, so you expose this, take this out, then move this over here,
Yeah.
and then move the
That
third
is
one
the-
over here, and then you're done.
Yeah.
Okay, this was even easier than I thought. Yeah.
5 steps.
So, again, my point is that really these cases are not that difficult. Of course, this is case analysis, and you have to write code for 12 cases at least, as far as I can tell. That's not that's not too bad, no?
I would have, even knowing this, I would not approach it.
No?
No. It
Why not?
It seems like one of the time wasters.
If you write one of the cases, you're pretty much, the rest should just be writing similar code, no? If you write a code for move, that's all you need. At least that's what I think, yeah.
Before starting, like we have to store like which should go.
You're still worried about
Like, it looks more realistic to me rather than.
Sorry?
It looks like I can see, so I can think how to do. Like in coding,
Yeah, he's thinking of the actual code.
I understand, yeah. But my point is that what I'm going to build is a data structure that says for every color, I build a configuration.
okay, so you have to store and.
Yeah, you need to
Yeah.
get
And
the
that
application.
comes automatically because let's say I scan through all the tubes. So I look at the first tube, it says yellow, blue, red. So yellow is on 1. So I'm going to put 1 in the yellow one. Blue is 2, so I'm going to put blue in as a 2. And then the red one is 3. So I'm going to put in red, I'm going to put a 3. And then I have to add in some more information saying it was in tube 1. Once I have this information, then I have to figure out of all the configurations, I have n configurations, which color should I work with? And for that, I'm saying pick a color that has at least 1, 1. And we know there is going to be. And then all these cases will take care of it. Right? That's the plan. Ricky still doesn't like it. Yeah.
It was the fourth least solved problem.
Sorry?
The fourth least solved problem.
Yeah.
Only 11 people got it.
I mean, it's like,
That's still 11 people too many. No, I think the reason people didn't approach this was because it ends up being case analysis, and case analysis can, they
Yeah, kind of
get
brute
messy,
force.
and you have to write, and you have to make sure you don't make mistakes because you do cut and paste, and
Yeah.
somewhere if you don't write one of the cases properly, if you miss one of these equal to or not equal to, then it could
yeah.
cost you lots of headache, and
It's
debugging
one
it is not
it's
easy.
gone.
And how do you set up data tests in order to make sure that all the cases are considered? So all this is, I mean, this is why people don't approach this problem. But my point is that it is doable. It probably is an hour's work. And you could easily divide the cases amongst yourself and attack this. If you do the analysis for a couple of these cases, then the rest are actually very, very similar.
So is this problem in the coding, they have space complexity, like space limitations or no?
Of course, there are space limitations. It's whatever machine you're running it on, and they provide the environment. So it's whatever IDE you're using, and I think they have I forget, they have the standard IDEs, and so you have the space limitations that come from the IDE. And yeah, it's not it's pretty large, but it's not infinite.
It's 1,000 megabytes.
Sorry?
1,000 megabytes.
Okay, so 1 gig.
Yeah, pretty big.
Yeah. But you can't put more than 1,000 by 1,000 array, for instance, right?
You can do 1,000 by 1,000.
Oh, sorry, it's 1 gig. Yeah, okay, right. Yeah, you can't do 100,000 by 100,000 array. Other questions? So you guys wanted to see what? I forgot.
Yeah, cookie.
Cookie, yeah. Wait, I didn't do it. Oh, shoot. Okay, let's just open the problem.
But time.
time's up. Yeah, so why don't you guys think about the cookie problem? We'll do it next time. So your team did solve it.